Well, hello everyone. I wish I could be with you, but unfortunately term has started here and so I'm bound to my teaching back here in Scotland. But anyway, I hope you're all having a great time in South Africa. I would love to come back someday. Today I'm going to talk about an interesting new class of object that was discovered by the Kepler K2 mission among the late type M dwarfs in the Pleiades. And these things show extraordinary short period dusty dips repeating on the timescale of the stellar rotation. So what I'm going to try and convince you of today is the conclusions of some very interesting work done by Hannah Sanderson, who was a summer intern here a couple of years ago. And she recently published this work, which suggests tentatively that what we may be seeing in these M-dwarf systems is some evidence of disintegrating sun-grazing comets. But let me take you through the observations and the logic first. The discovery of these things dates back to 2016, when Louisa Riebel and John Stauffer and others were carrying out a rotation survey of late-type stars in the Pleiades. And this was using K2. And among the stars with spectral types later than M5, there was, as usual, a population of extremely rapid rotators with spin periods of order half a day or less. And if you look at the rather compact data here, what you see is the light curve plotted against time. You can see that this one is bimodal on average, long term, but it has a single spike in its periodogram. And if you phase fold the data on that period, you get this extraordinary pattern of dips, which are far too rapid to be caused by star spots. There's also an underlying modulation, which is the kind of thing that you expect to see from star spot activity. The late John Stauffer actually nicknamed this particular object the Batwing star for reasons that I hope will be reasonably obvious. But it's by no means the only one, and a large number of these late type M dwarfs show either single or multiple periods, but all of these periods are less than half a day, and the dips, when they occur, are very much too fast to be explained by star spot modulation, which seldom produces anything more than 2 bumps in a light curve. So these were also seen subsequently in younger star-forming regions with K2 and later on with TESS. And there's a sequence of papers by Louisa Riebel in 2018 and 2022 describing how objects of this kind have been found in Upper SCO and elsewhere. But in the TESS era, some of these have been found in rather remarkable places. And this one in particular was the subject of a study by Max Gunther. It had the good fortune to be very close to the ecliptic pole. So it appears for a full year in the data from TESS Camera 1. And so what we see on the right here is a year's worth of data, 13 sectors, and each TESS sector has a pair of 13-day segments in it. And so here, Max Gunther has phase folded the light curves obtained during each of those 13-day segments. And so what we see is quite a stable underlying slow modulation of the kind that you expect to be originating from star spots. But sporadically, you see features like this, and they last for about, I call it 3 fortnights. Okay, so on the order of weeks to months, we see these features appearing and disappearing, but they're very much narrower than the broad modulation that you expect from the underlying star spots. But the curious thing is that they have exactly the same period. So whatever is causing them is rotating at the same rate as the star. So what causes them? There are 3 favored theories. Bodman et al. In 2016 suggested that we might be seeing some form of irregular dust structure in an accretion funnel where the inner edge of the disk starts feeding dust down the magnetic field lines onto the star itself. Remember that these stars are later than M5, so in fact the dust sublimation radius is pretty close to the star. John Stauffer and I favored an explanation involving co-rotating clouds, and that's what I'll be concentrating on in this talk. So again, you need clouds of material that are, by design or coincidence, at the co-rotation radius of the star, or at least held in co-rotation, perhaps by the magnetic field. There's also a slightly more complicated model by Jeanne et al. In 2019, involving a tilted accretion disk, or at least a disk tilted to the line of sight, which periodically occults star spots rotating across the obscured part of the stellar disk. The problem that John and I had with this model is that if the star spots are dark, if they're obscured, the short duration bumps that they produce will actually be bright. So Hannah came to us to work as a summer intern, and I set her to work on the analogy with stellar slingshot prominences, which is something that we see also in the young open clusters. Thinking back to the last time I visited South Africa, it was in fact to observe this phenomenon at Sutherland, which is the phenomenon of stellar slingshot prominences. And these are common in ultra rapidly rotating young G and K dwarfs, such as, well, the prototype for this is AB Doradus, but also other objects such as Speedy Mick and other G and K stars of the age of the Alpha Pur and Pleiades open clusters show this phenomenon. Unsurprisingly, being fast rotators without a convective zones, they're covered in star spots, which you can see in time sequence spectroscopy of the kind that we do in Doppler imaging. And what you see moving across the star here from blue to red is the bright trails left by dark star spots as they transit the stellar disk. Now, these appear in all of the metallic absorption lines in the star. But if you look in the Balmer lines and the calcium H and K lines, you see something rather different, which is on the same time scale, because we have phase, a complete rotation going from 0 to 1 up here. This is actually Speedy Mick, which was observed in July 2002 and modeled by John Barnes, and the H-alpha work was done by Nick Dunstan back in 2006. What we see here are dark absorption transients moving across the face of the star. And what we believe is happening here is that clouds of neutral hydrogen at the sort of temperature that you see in solar prominences are whizzing across the star, and the greater radial acceleration that you see going across tells you the distance of the object from the star. And it turns out that these absorbing features are located very close to the co-rotation radius. And the short duration of these events is, to my mind at least, a possible explanation for the short duration of the dips that we see in these late type M dwarfs. The trouble is, they don't absorb in the continuum. So the thing that we have to then explain is how you could have prominences that are full of dust. And so this was the problem that we set Hannah Sanderson to work on. And I have to say she did a magnificent job, and you can read all about it in her paper in Monthly Notices published last year. We needed a prototype M5 star, so we chose V374 PEG, which is an extremely rapid rotator, which has been Zeeman Doppler imaged by Jean-François Donati and his team back in 2006. And so Moira Jardin, who's also an author on the paper, did the three-dimensional field extrapolation from the surface magnetic field map produced from Zeeman Doppler imaging. And so this is what it looks like. It's approximately dipolar, but if you calculate where you expect to get gravitational and magnetic potential minima, because of course if you spin this thing fast enough, eventually you get out beyond the corotation radius and material will pool at the summits of the field lines. So then the problem arises of how you trap dust. And so Hannah followed a very elegant physical argument advanced in a paper by Kay and others back in 2012, whereby if you put dust into a stellar corona, it's being hit by electrons traveling at many hundreds of kilometers per second. The electrons travel faster than the protons, so you get more electron hits than proton hits, and your dust becomes negatively charged, which allows it to be confined near the loop summits. And these loop summits were actually mapped by Rose Waugh, who's another of Moira's students, in a paper published the previous year. So to test this idea, we looked at the distance limits of the clouds from the star inferred from the transit duration, because unlike H alpha, we can't measure the radial acceleration of these things spectroscopically, but the transit duration gives us at least a lower limit on the distance of the cloud from the star. So the straight line here is the location of the corotation radius. So on the x-axis, we have the corotation radius for a bunch of stars with slightly different rotation rates, studied by Jean et al. In their 2019 paper. And on the vertical axis, we have the measured lower limit on the cloud distance measured from the transit duration. And we see that for the faster rotators, these things cluster near corotation. Further out, they could be at corotation, but we actually see them apparently further in. But within a factor of 2, that's roughly where they are. Hannah worked through the physics of dust confinement, which I don't have time to explain to you in detail here, but the idea is that you need enough Lorentz force to be able to confine a dust grain of a given size and charge against gravitational collapse back down the loop. By putting agglomerations of dust at the potential minima, it was possible to synthesize light curves. And here we see the synthetic light curve from one of those 3D models. And you see these short duration dips appearing in the light curve where the optical thickness of the dust is sufficient to actually give you these short-lived dips. So the lifetimes of these things tell us something about the lifetime of the confining structure or the time-dependent nature of the confinement process. It may be that these things build up and then break out. The total amount of dust needed to give an optical depth of 1 depends on the size of the dust grain, but for sizes between about 1/10 of a micron and 10 microns, the mass of the cloud ranges from anywhere from 10 to the 9 up to about 10 to the 15 kilograms, which is kind of interesting because the typical mass of a rubble pile asteroid is about 10 to the 14 kilograms. So that got us thinking about how the dust gets there, because only a few % of these fast rotating M dwarfs actually show this phenomenon. So if it were a disk-like structure, then we would only have a small minority of them showing the phenomenon because of the viewing geometry. But the sporadic nature of these structures that we see here suggests that the dust supply is probably sporadic, which led us to think about the possibility that we could be looking at some form of disintegrating sun grazing, or perhaps I should say star grazing cometary bodies. So I'm going to leave you with a lot of open questions because this is a very puzzling phenomenon, but obscuration by magnetically confined corrotating dust does appear to hold water as a physical explanation for how these dips arise. And there is a strong analogy with the slingshot prominences, but the question then is, how do you get the dust into the potential minima? Where does it come from? The stars in the Pleiades don't appear to show any infrared excesses that would indicate residual disks. So one possibility is something like this phenomenon here, which was observed by the LASCO instrument on SOHO back in 2013, where comet ISON flew in and, like most sun-grazing comets, was expected to evaporate completely, but in fact didn't. It disintegrated, and its dispersing remains were seen coming out from the sun on a nice parabolic or hyperbolic orbit. So why do we only see them in late M dwarfs? It's probably because they're cool enough that the dust doesn't sublimate during this process. Why do we see so few? Well, if they only receive dust every time a sun-grazing comet comes in, then you've naturally got a sporadic injection mechanism into the corona. But that, of course, leads to another question, which I'm going to leave open, which is, if it's caused by comets, what puts them in those star-grazing orbits? Is it possibly a signpost that there are giant planets somewhere out in these systems? Sadly, at 16th magnitude, the Pleiades ones are a bit too faint for spectroscopic follow-up.
Your injury time is over, Andrew.
And well, that's absolutely perfect timing, Patricia, because that's the end of my talk.
Thank you very much.